One of the most imagined scenarios by most people is a space catastrophe involving a star being swallowed by a black hole. Fortunately, the chance of a black hole wandering around in our solar system is very small, which is good news. But what if it's already here, hidden at the center of the sun, slowly consuming it from the inside out? In the past, we actually thought there could be a black hole at the heart of the sun. And when I say thought, I refer to a small group of scientists that, at least for a while, included Stephen Hawking. He mentioned in a 1971 paper that we would never know if the sun were hiding a black hole with a very small mass. It seems unlikely, as black holes should have masses at least 20 trillion times larger or even more than our sun. However, in the same 1971 paper, Hawking also discussed the possibility of several much smaller black holes that could have been created in the early universe, now called primordial black holes. Today we'll address this recent idea suggested by research, stating that if our sun or any other star has captured a primordial black hole, what would it do to the star? How would we find out it's there? And also, how could it even explain the origin of mysterious dark matter? First, let's talk about why Hawking's idea caught the attention of several astrophysicists. This happened because a black hole at the center of the sun would solve a major mystery about the behavior of our star. Until about the middle of the last century, we thought we understood very well the fusion reactions that power the sun. This included the temperatures and pressures we knew existed at the center of the sun, causing hydrogen to fuse with helium in the right amount to produce the energy that fuels it. These reactions should also release many neutrinos into space. Confirming if the sun was emitting the right number of neutrinos would be our sure confirmation of our model of its interior. The first neutrino-detecting devices started operating in the 1960s, but the number of neutrinos was much lower than expected. This led to what they called the solar neutrino problem. One suggested solution is that the sun doesn't generate all its energy through fusion. Perhaps some of the sunlight comes from a source that doesn't produce neutrinos. Later, Hawking's idea about black holes inside stars emerged, along with a possible new energy source for the sun. You might think that a black hole sucks energy from a star instead of providing energy, but that's not quite how it happens. Black holes are indeed the most efficient engines in the universe. While the matter and energy entering the black hole are lost forever, the approaching matter can reach speeds close to the speed of light, resulting in intense friction and high temperatures. Thus, a black hole feeding shines brightly. For example, quasars powered by giant black holes in a feeding frenzy are among the brightest objects in the universe. A black hole at the heart of the sun would consume part of its matter, but much more would be expelled as radiation. In this way, the sun wouldn't need to fuse as much hydrogen to produce energy, and therefore, it also wouldn't produce as many neutrinos. This idea was intriguing, except that later we discovered the true reason for the solar neutrino problem. The sun was actually producing as many neutrinos as we expected. We just weren't detecting all of them. Neutrinos oscillate between 3 different types, and our detectors were only sensitive to one type of these neutrinos, with all of them being correctly accounted for. The black hole engine was no longer necessary, and that might be good news, but there's still the persistent problem that if primordial black holes exist, some may end up inside stars without us knowing. In the decades following Hawking's paper, we found more reasons to believe in the actual existence of primordial black holes. Before we delve into black holes within stars, let's quickly discuss these reasons. This isn't a new idea, and in fact most mass ranges in which these black holes could represent dark matter have been ruled out. However, there's a remaining mass range of very small primordial black holes generated in the early universe, which could reach masses of medium to large asteroids and haven't been ruled out by observations yet, so they could be dark matter. If dark matter is composed of these primordial black holes, then it wouldn't be absurd for some of them to end up inside stars. Another reason to consider the existence of many primordial black holes is the observation of gravitational waves. Currently, we detect hundreds of black hole mergers through the small disturbances in spacetime generated in the last second of their spiral. Although these mergers typically involve black holes formed in the deaths of massive stars, there are some curious inconsistencies regarding the type of black holes we would expect from these stellar deaths. These inconsistencies could be explained if some of these mergers involved primordial black holes. So, there are reasons to think that there might be many black holes out there. But the implications of one entering the sun are quite interesting, and that's the point we'll explore next. Two recently published articles on Arxiv investigated this possibility. Both papers presented advanced simulations of sun-like stars that captured primordial black holes during their formation and tracked their evolution through unique life stages before eventually being engulfed by black holes. These black hole-harboring stars were dubbed Hawking stars in honor of the physicist who introduced this concept. For many decades, the evolution of stars into black holes was well understood. Where a large gas cloud collapses under its gravity until the core reaches pressures and temperatures high enough to initiate the fusion of hydrogen into helium. Thus, the star is born, and the core sustains consistent fusion for billions of years. When the fuel is depleted, the star goes through several phases until becoming a white dwarf, leaving its core exposed. Now, when we add a black hole to the equation, the articles simulate what happens if a primordial black hole with the mass of a medium-sized asteroid is present in the gas cloud where the star forms. This also works for a star that captures a black hole after its formation. A black hole with this mass is tiny, the size of an atom, and its gravitational reach is limited. Therefore, it doesn't affect the initial formation of the star. It sinks to the star's center and begins feeding slowly. The energy produced by the falling material radiates outward, altering the state of a small region at the core's center, covering about 1% of the star's radius, equivalent to approximately the size of Earth. Within this region, the material, which is usually relatively static, begins to violently agitate. This effervescent ball grows as the black hole grows, eventually consuming the entire star. But this won't happen for a very, very long time. You might think that with an uninterrupted supply of matter, the black hole would grow rapidly, but that's not the case. The radiated energy near the black hole actually pushes against the new material falling, severely limiting the black hole's growth rate. The tiny size of the black hole also makes it a bottleneck, creating a limit to how quickly you can compress matter into an atom-sized black hole. This initial rate is something like 100 tons per second, which may seem like a lot, but it's basically negligible. For comparison, the Sun loses almost 1 million tons per second to the solar wind. But as the black hole gains mass, its gravitational attraction increases, as does its size. Then, the bottleneck widens, and the material flows more easily. It also emits more energy but still faces some limit to its growing appetite. The rate of fusion reactions throughout the rest of the core remains more or less constant. This means that the energy supplied by the black hole represents a growing fraction of the star's total energy production over a few billion years. This atom-sized black hole grows to about 10 centimeters in diameter with a mass similar to that of the planet Uranus. At this point, a significant transition occurs. The energy output from falling material is now roughly equal to the fusion output from the rest of the core. As we approach and surpass this point, the effects of the dark secret of our Hawking star become much more evident. This additional energy disrupts the delicate balance between gravity and outward energy flow, causing the star's outer layers to expand. This would make the star appear to enter its giant phase billions of years earlier than expected. In a normal giant phase, the star's core remains compact, but in this phase for a Hawking star, even the core expands. The density drops so much that fusion is completely halted, and now the star operates entirely on the energy from the black hole. During this phase, the Hawking star appears like a regular dying star, at least initially. Our Sun will expand to about 100 times its current radius, and will be 1,000 times brighter, but a Hawking star stalls before getting that large. The initial expansion makes it much harder for the black hole to feed, limiting the growth of both the black hole and the surrounding star. It reaches a size about 4 or 5 times the current size of the Sun, shining about 10 times more intensely, possibly appearing for up to 10 billion years like a relatively rare star before the black hole finally finishes consuming the star. So it is possible to think that there is at least one positive aspect to the Sun containing a hidden central black hole. Although it has less time as a normal fusion-dominated star, it won't actually swallow the Earth, which is likely to happen during the red giant phase. To move this theory out of the realm of pure speculation, researchers started to analyze a few things. Overall, if there's a black hole in the Sun, it must have a mass smaller than that of Mercury. More than that, and the Sun would already be expanding. But what about a smaller black hole? Well, it would need to be much less massive than Uranus, or we would have noticed signs that the Sun's behavior isn't consistent with all its energy being produced by fusion. For instance, despite knowing that the Sun is basically producing the right amount of neutrinos, if all its energy is coming from fusion, there's some uncertainty in neutrino measurements. Up to 1,000th of the Sun's energy could come from a source unrelated to fusion. An embedded black hole would also alter the core's temperature and pressure, and hence its fusion rate, affecting neutrino production. However, these studies don't reach the deeper regions of the core, meaning we wouldn't have noticed the effect of a black hole with about 1/1,000,000th of the Sun's mass, based on current observations. The probability of our Sun harboring a black hole is extremely low. However, if primordial black holes exist in the correct mass range, it's likely that some of the billions of stars in the Milky Way have captured one. In this case, some of these stars should be in the swollen phase of a Hawking star's life. From Earth, they would appear indistinguishable from certain rare types of stars in the giant phase, at least in terms of colors and sizes. However, these swollen Hawking stars would vibrate differently and could be detected very easily, as stars without a complex interacting core would have simpler vibrations. Although candidates haven't been identified yet, potential data to detect these signals has already been collected in the latest release of the European Space Agency's Gaia satellite. The team is committed to investigating this as soon as the data is made available, And some researchers bet that even if this possibility is low, they wouldn't be surprised to find stars out there shining a little brighter than expected as they are consumed from the inside out.